Welcome to the ET380 lecture video on electronic test equipment. Okay, there are two types of oscilloscopes, analog and digital. And the digital have several different scopes. We have DSO, digital storage oscilloscopes, that store and capture signal for later analysis. A digital phosphor oscilloscope that uses digital screen with high resolution, and we have a mixed signal oscilloscope that combines analog and digital capabilities. We also have an MDO, which is a mixed domain oscilloscope, which simultaneously displays the same signal as a time synchronized time domain and frequency domain traces. We also have a digital sampling oscilloscope, which employs equivalent time sampling to capture and display samples of a signal, ideal for accurately capturing signals whose frequency components are much higher than the oscilloscope's sample rate. Here I'm showing the oscilloscope that we use in this class. It's also available in our classroom and in Multisim. And this one, oscilloscopes are a time versus amplitude device. The amplitude we could adjust with these 4 channels, and our time we could adjust with our seconds per division knob. Our oscilloscope allows us to use cursors, which we could do time or voltage, and we also have a math function that'll actually display different times and frequencies. Our oscilloscopes also have a fast Fourier transform, FFT, where we take the signal in the time domain and we convert it to a frequency domain. And here is a plot of that. Here's a fast Fourier transform of an AM signal. So here we show it in the time versus amplitude, and here we have frequency versus, and you can see the main frequency and our 2 side bands. Okay, let's take a look at our spectrum analyzer. In it, as our oscilloscope looks at time versus amplitude, our spectrum analyzer is going to look at frequency versus amplitude. And it is an excellent tool for doing troubleshooting and design. Here is a spectrum analyzer plot, and we see on this side we have decibel amplitude, and on the bottom we have frequency, and we can see the highest frequency here at 1K, and then we can see a 2K and other lower frequencies. So we can analyze and tell which frequency and what the amplitude is. So we can do signal analysis with a spectrum analyzer, and we can use the frequency spectrum of the signal to help identify the source of interference on a particular frequency. For voice and data communications, we'll identify the source of the signal's interference or inability to meet performance requirements. For video broadcast, we can use a spectrum analyzer to ensure the transmitted signal is strong enough to reach its intended destination. We use it for radar to help determine the range, velocity, and direction when tracking an object or navigating. In wireless technology, we could use a spectrum analyzer to identify the best channel for a wireless router or access point when Wi-Fi testing. Vector signal analyzers, or VSAs, they allow you to design, validate, and debug communication systems. They provide insight into the behavior of these systems by providing measurements of the signal's amplitude, phase, and frequency. VSAs also offer advanced analysis capabilities such as time domain analysis, eye diagram analysis, and modulation analysis. These capabilities make VSAs invaluable for ensuring communication systems meet their performance requirements. VSAs are available in various forms, including benchtop units, modular units, and handheld units. Here's a display of a vector signal analyzer, and here we see a QAM dots, and we have the outer circle is the limit set, and here is the vector diagram showing a well-designed system because all of the areas here around our dots are within that error circle. And this is the only way that these complex signals can be analyzed. Here I'm showing a very basic function generator. And this guy will do sine wave, rectangular waves, and triangular waves. And we could adjust the amplitude and we could do an offset. But this is a very, very basic function generator. Okay, the function generators we use in our classroom and in multisim, we'll add our basic waveform, plus we could do TTL, transistor logic, CMOS, which is a digital signal where we can control the amplitude of the signal, and we could also change duty cycle, and we could actually combine signals with connections in the back. Here's an arbitrary function generator, which is an advanced function generator, and it'll do the basic signals, and it adds AM, FM, FSK, and others, and it can be programmed online or with software, and it could produce just about any signal. So this is a very handy tool. Here I'm showing a radio communication service monitor, and its tool is to automate radio tests and alignment functions, offer capabilities like high power RF sensors, vocoders, and advanced digital test features essential for land mobile radio technologies. So this tool includes a signal generator, spectrum analyzer, oscilloscope, channel analyzer, power meter, and other analog and digital radio test functions into a multi-purpose standalone instrument. And we have these both at the school, and these are the signals that it'll test, including the new P25 digital radio standard. Here I'm showing a time domain reflectometer, TDR. It's using techniques to verify the impedance and the quality of signal paths and components, interconnects, and transmission lines. And it works both with optical fiber optics and copper, and it's a very handy tool for troubleshooting and measuring distances. Here's a simple diagram of a TDR, and what it does is we send a pulse, a signal, okay, down the line. So we could tell by its reflection, is it open circuit, it just keeps on going. A match load, which is what we'd like to see, is that it's the load and the cable is matched. Or it'll tell a short circuit and how far that is out. Here's a diagram showing different applications of a TDR, and we show the signal sent out and the reflected result. So if it has a negative pulse, we have a shunt capacitor discontinuity. If we see a positive, we have a series inductance discontinuity. And if we see a high and low, we get a LC discontinuity and a CL discontinuity, showing that the minus first and the plus after that. And we have a CLC discontinuity and an LCL discontinuity and a capacitive termination and an inductive termination. So this is a very useful tool. Next is a SYNAD meter. So SYNAD is signal to noise and distortion meter. It's used to measure radio receiver sensitivity performance. It's used for FM, VHF, UHF, and others. It's good for finding signal degradation issues into a single measurement. And so the overall measurement of the system performance can be assessed. The next is a rubidium standard time reference. And this is an atomic clock. And it's a frequency standard specified to hyperfine transition electrons in rubidium-87 atoms used to control the output frequency. So this is used as an inexpensive, compact, and widely produced atomic clock used to control the frequency of television stations, cell phone base stations, and in test equipment and global navigation satellites like GPS. Okay, next is a network analyzer, and this is not computer networks. This is a multiple port analyzer for communication. So we could find S parameters because reflection and transmission electrical networks are easy to measure at high frequencies. And we could also measure Y parameters, Z parameters, and H parameters. So a network analyzer uses to characterize two-port networks such as amplifiers and filters, but they could use on networks with an arbitrary number of ports. So we can analyze different components in a communication system. Here's a frequency counter. It's an electronic instrument used to measure the frequency of an input signal, and it's typically displayed in hertz, cycles per second, and it works by counting the number of cycles or pulses in a signal over a specific time period.